Unparallel doesn't have any assumptions about the engines being in the same location, the engines being able to talk to each other at all. They're just IPython processes somewhere in the world that I have a socket connection to via SSH tunnels or whatever. So we make no assumptions about where the engines are relative to each other. Plus, all the logic for talking to multiple engines is in the client, not in the controller. So I'm going to create a client. This will take a second because it is far away. And this is a useful, very useful utility. So async results, or when you get the result, it's a list of the same shape as targets when you call get. If you call get dict, instead of a list, you get a dictionary keyed by the engine ID. So I just called socket.getHostname and then called getDict. And now I have a dictionary that tells me the host name of every engine keyed by engine ID. But that's not actually the question I want to ask. The question I want to ask is, show me the engines on a given host name. And this is just inverting that dictionary. So now I have a dictionary of host name where the values are the engine IDs on each host. So this lets me do things like I want to do an operation. I want to confine this work to this machine. And I have all the information I need to know. I can do, I could create a view. Right, so I just created a view that's only looking at engines on one host. So if I do so everybody gets the same answer. You don't trust me? They were started. They were started. So these engines were started with MPI. So they were started kind of all at the same time. Yeah. Yes. So that is actually controlled by the MPI configuration on the cluster in this particular case. So what I did, there's an MPI hosts file on the cluster, and what I did to start it. I can go into some of the configuration I used. Yeah, pretty much. Like PBS or SGE, all the batch file things will say, this many nodes per, this many processes per node, this many job IDs per job array should go on a node. MPI uses a hosts file. So the way these engines were started was actually SSH to the cluster, MPI exec. That's all I needed to do. It's not in a batch system. It's just direct to MPI. And MPI picked which hosts to run it on. And so here's the reason why we would do this. I'm going to create a not very big array. I'm going to just check what's kind of my overhead for just talking to this cluster at all. This is saying every engine is basically ping. This is the IPython parallel version of, hey, everybody, are you there? It's just call a function that doesn't do anything. And so that took a quarter of a second. Ping just one? 1A or one engine or one set of engines? Okay. Yeah, so we can see there is actually, because of the naive design of IPython parallel, just saying do a no-op on everything is an order n operation. Because it's actually, the client is saying, engine 0, don't do anything. Engine 1, don't do anything. Engine 2, don't do anything. And then getting the results. So now I'm just going to do a simple push. I want everybody to have the same data. Question?
Yeah, so you said you've done, so here you instruct one on I and it goes to next node.
Uh-huh.
The other one goes to node. The ones that we're doing, that you said don't do anything to, do they have to be ready for?
No. So because of the 0MQ magical async networking nature of things, I just send a message. So I just iterate through and send a bunch of messages. And that actually doesn't even correspond to a network send. It actually corresponds to handing off a pointer to a background C++ thread that will send when it feels like it. And then that's also happening on the engine side. It can be doing big blocking NumPy GIL operations, and those messages will actually be can queue up in memory on the engine because the messages will arrive in GIL-less C++ 0MQ threads. So receive is often just copy a pointer, take control of a pointer from a C++ thread to Python. Yeah, so when that's why the async, when I do an async poll, it's actually saying send a request for data, and the reply will actually come, and when I do async result.get, that's actually just grabbing the data that's already waiting in my process's memory and then just turning it into Python stuff. Yep. Yeah. All right. I should have been talking while waiting for this to happen because this. So I'm just pushing, doing the naive push, the order n push. I'm pushing a 256 square array. This is not a lot of data. But the network is not awesome, and I've got a moderate number of engines. This is taking an unreasonable amount of time for the amount of data I'm moving. The controller is running on the cluster. Yeah, so if you think about the structure of what push does, is the client, for each engine, sends the data to a scheduler, and the scheduler relays that message, sends the message to the scheduler, and the scheduler relays that message to an engine. So I'm actually sending, between the client and the controller, I'm sending the same data n times. And then the controller, or the scheduler, is sending the same data n times to the engines. This is the consequence of, one, the naive design of IPython in terms of there are no broadcast primitives or anything, and two, the design of having the multiplexing logic be in the client rather than in the scheduler. So those two things are conspire to make this super slow. On what? You'll see. You'll see. All right, so import NumPy. So this demo is going to assume, I'm not going to assume anything about the cluster. It's just these are host names. All I know is I know that all the engines with the same host name are one machine. So what I'm going to do is instead of sending the array over the network to every engine, I'm going to send it one time to every engine, and then I'm going to load it on all my engines with memmap. So NumPy supports mem-mapped arrays, which is basically you write data to disk, and then NumPy loads it, loads the data on disk as if it were in memory, and then brings it into memory as needed. So what I do is I have a broadcast with memmap, takes an array, it takes a name that I want to store it in, a parallel client, and then the host map, this mapping of host name to engine list. And what I do is I iterate through those engine lists. I grab the first engine on the list, and then if it's here, I just write it to a file. I don't send it anywhere. I just write the array data to a file. If it's anywhere else, I call apply with this array to file. So I send the array to one engine per host and write it to a file. And in this, it just creates a temp file and then returns the file name. So after this stage, I have a dictionary by host name of file names that contain the data. I've pushed my data one time per host. And then once I've done that, I iterate again through the list, and then on every engine, I get the file name. So these are async results, so I use async result.get. So this is actually where the waiting happens, is on this line. And then, so the engines are the lists per host. So I create a view of just the engines on that host, and then say, all you load that array from the memmap file. So this is instead of, if n is my number of IPython engines and m is my number of physical machines, then I'm sending the data m times instead of n times, and then I'm loading it from disk n times. So now let's see how long it takes to broadcast with memmap. Remember, it took, where did that go? It took a minute. No, it took 22 seconds. Oh, that was a millisecond, yeah. 22 seconds to do the big dumb push. And now if you do it with BCAS, okay, it took 2 seconds. Right, which makes sense because instead of the main limiting factor would be, these guys. So instead of sending it 50 times, I sent it 5 times. And then with a little bit of overhead for the memmap load. But
presumably this is going to work in a slightly modified form if all of the computers have a shared file system.
yeah, if they're on a shared file system, which is actually the case here, instead of sending one per host, you send just one. The real thing, so the key that you want to map onto is basically data store. So IPython itself assumes nothing. It operates on the assumption level that engines can't talk to each other at all. They're totally isolated. And then with the host name thing, you can reasonably assume that multiple processes on one host can read from the same file system. If you know that they're on a shared file system, then you would use the key that you use for this host map. Instead of a host map, it's more like a data store map. The key that you would use is like this shared file system. These engines have access to this file system. So I could have half my engines on this big compute cluster, and then the other half could be on my workstation on my desk. And then I would send once to my desk, once to the cluster. And then just to verify that the array is actually the same, I can compute the norm. So I did, in fact. Yeah?
Again, maybe a bit off topic, but the name temporary file, because presumably, or quite often we have a much faster Scratch.
Yeah, you put it on Scratch. There may even be on Scratch. So this is Brian's the physics cluster at Cal Poly. I don't actually know anything about it. I got an account from Brian. So yeah. So the more you know about the system, the better you can do. But the important thing about this is that just because IPython is slow, doesn't mean you have to be slow with IPython. That would be fine. The file actually doesn't exist on my file system. But yeah, if it started out as a file, then that would be fine. The main thing is use, just because IPython has, because it really is IPython, it's a full interactive shell on the system. If you have any way of getting data to those machines, whatever the most appropriate way to get data there is what you should use. But just because you're using IPython doesn't mean you should use IPython for everything. And so a similar example, solving the same kind of problem. So now we're moving data. I can increase my assumptions. I actually did start all of my engines with MPI. So I know that those engines can talk to each other really, really efficiently. And if you want to test this locally, if you've got MPI all working, you can just start a cluster with, so engines equals MPI. This means IP cluster, instead of starting subprocesses with popen, you should start the subprocesses with MPI exec. So you can start do testing locally with MPI just with this line. And profile MPI just means run this cluster at the same time under a different profile rather than the default profile that we're using. You can, if you want, you can make the default behavior to start with MPI as well. Yep. Can you speak a little louder? Can I combine IPython with the multiprocessing module? Yes. Yeah, so there's, depending on the nature of your computational work, this is something I haven't really talked about, but the number of engines, the number of IPython engines you start per node, it can vary, right? So if your code that you're distributing is already strongly multi-threaded and will actually use a multi-CPU, multi-CPU, multi-core node, then you only want to start one IPython engine per host. If your code is naive, GIL-grabbing Python, it's really only going to use one thread. You want to start one. You're going to want to start one engine per nominal thread. Now that chips are hard to reason about, per thread on the per logical CPU, and then even beyond that, if your engines actually spend a significant time waiting for other resources, you might want to start more engines than CPUs or CPU threads per node. It just depends on what work you're assigning to an engine, what resources that can use, and that should determine how you allocate your IPython engines. Yeah.
Something a moment ago that caught my ear. You said you could have engines running some of the cluster and some on your workstation.
Yeah.
In the same cluster?
Yes.
And
How does that what?
How is it controlled? Do you set it up during when you start the cluster, or can you dynamically change it?
Oh, can I do this right now?
Sorry, I didn't think so.
No, let me try something. Oh, no, that'll ruin this. After this, I will try something that might totally fail. I think I can just add an engine on my laptop to the cluster where the controller is on this remote cluster. And it will be outside the MPI universe, but whatever.
If you've got MPI working locally, is there a reason not to just have your default cluster stay with the MPI one?
No, I don't think so. I think that should make at least as much sense most of the time. Oh yeah, that is a reason. Is that yeah, an MPI world is all or nothing. So if you want those to be a function of time, you know, if your code might segfault, you don't want to use MPI because one engine segfaulting will bring down all of its siblings. But you could, like, if I want to do, I can use one cluster with actually 10 different MPI jobs. So like all my engines have rank 0 to 4, but I've got 40 engines. You need to be careful with that.
Yeah.
I don't know why you would do that, but yeah, that's the one reason to not use MPI locally is the tolerance of bringing down engines. All right, so I've got my MPI cluster. Yes. So now I'm going to use MPI for Pi to talk to the MPI universe. And again, I use my getDict to get a mapping of MPI rank to IPython rank because they're not the same. I create my same push again just to show this will again take 20-ish seconds. Or 12, whatever. So now I'm going to broadcast. This actually doesn't do anything. So I have a function that I'm going to apply. It takes a key. So this is the key to store. I want to send the data. So everybody, I want to emulate push. I want everybody to get data, my data array, into the variable data in the interactive namespace. So key is going to be the string data. And root rank is going to be the rank of the whatever machine I decided to make the. So MPI Broadcast is a function where everybody calls the same function, and you specify who the root is, and the root sends that data, and everybody who isn't the root actually receives. So broadcast is like a sync point across all your engines. And depending on whether my rank is the root rank, if my rank is the root rank, I send. And if my rank is not the root rank, I receive. And then I just store that object in the globals. So now the function I call locally is broadcast. I get the key that I want to store it in. I get the object I want to send. I get my direct view, that is a direct view on all engines. I get the root engine, or the view on the root engine. And then I get the root rank. So what I do is I push asynchronously, and then again asynchronously, I call broadcast everywhere. So this time, instead of sending once per physical machine, I'm sending once, just one time, and then everywhere I'm saying get the data from MPI. It is still an order in operation, but it is order of a small number times n. Yeah. So I'm still saying everybody do something, but that something is just call this function. What I'm not doing is everybody here is an array. I'm saying everybody here is a little bit of code to get an array.
You changed the little b and bcast to capital B.
But if you had this embedded in a much larger bit of code where you knew at this stage in the calculation everyone was going to broadcast it on, you wouldn't have that overhead cost. The overhead cost is because you're hitting this.
The order n cost is due to IPython, not MPI.
MPI can do this in a log and log too.
Yeah, so actually, the expensive operation is moving the data around. This is entirely dominated. Roughly all of this time is spent in push, the one push. The broadcast is, for 50 engines, is roughly negligible. It's not negligible anymore if you're at 200 engines. You don't want to use IPython parallel for more than a couple hundred. It's hard to do. It's hard to imagine too much interactive scale work with 50,000 nodes. But yeah. Yeah. Yeah, I've got a. There's a notebook for that. I only copied one, but yeah. So let's say, so I'm going to start a cluster locally. No, I'm not going to use the remote one for this. So the command I started before was ipcluster start, and I'll just do it in terminal. No, you'd have to background it.
Even running it in the background.
Well, I'm going to run it in terminal, so I don't need to know.
But I was wondering if you were doing the terminal just for fun, or.
No, I was only going to type it. I wasn't going to run it there. So I'm starting. Where did everything go? There. So I'm starting 4 engines with MPI and writing the connection files to my MPI profile. And hopefully I don't have broken MPI. Okay. So here I've done activate 0, so I've got PX for engine 0. Got a basic client. Let me sure I've got stuff. So now I'm going to emulate having some parallel MPI program. This is just some utilities for getting the MPI order of things, since the IPython rank is not the MPI rank. So this is a toy simulation, an MPI program that runs. Oh, I should have copied the other one. This is the. Is this one? Yeah. Anyway. So a toy simulation that just runs. It's got variables. It computes sine of function of x squared plus y squared. So it's just a function that evolves slowly over time. So I can plot current results. This is a function that does a pull of z. This is the state of the simulation. And concatenates it into, it's like gather, but gather doesn't have a reorder. Actually, you could do that with a view. So this is basically gather of z. And then it plots the current state of the simulation. And in this case, right, because in this case, I'm actually running the computation in a thread. There's two versions of this. There's one where you run the simulation in a thread, and then you query it. And the other is where, with IPython, you call step. So the state of the simulation is static, and then you make an IPython execution that says everybody do 30 time steps. Make sure. So monitor function just does, while true, check on its status and plot. This is spawn a thread to run the simulation, right? And that returns immediately. I can monitor it. This is an actual MPI simulation that is running and refining a mesh. And then I can stop it, because since it's in a thread, I can stop it.
You can stop the monitoring, the simulation. The idea is to allow you, this is work that we did with some of Chris Aaron's colleagues, that if you have, normally getting data out of MPI is a bit of a pain in the neck, and you have to write a lot of logging code and whatnot. The idea here is to let the MPI code run by itself, and you periodically send data over to the notebook for plotting purposes. And what Min interrupted there, you can stop and start the monitoring, which is completely separate from the MPI code. So in this case, the issue was an MPI simulation that could, for monitoring purposes, the only place where they could run it was by moving it to a workstation that was beefy enough to run the parallel code, but they had control over, so they could have visualization tool libraries in it, because in the supercomputing environments, you couldn't have visualization code. So what this lets you do is you run the simulation wherever it wants to be run, in this case on a supercomputing machine, and then just grab the data and visualize it on a laptop in the notebook, and decouple the two issues and the time step of the simulation from the time step of the monitoring, have them be decoupled by letting MPI do its thing, and using the IPython APIs for what they're good, which is kind of this more interactive control. So this is not competing with MPI, but sort of collaborating with MPI to make one aspect of your life easier, which is the part that MPI doesn't do very well, without trying to get in the way of the fast. In this case, I mean, this is a toy example. The real world problem was a parallel fluid dynamics code written in a combination of C++ and Python.
But you could also, so in this version, he's just monitoring, but for biz geeks here, the second side of this is steering, right? So not only can you look at what's going on, you can inject back in.
Actually, that stop is doing that. I mean, in this case,
The steer is the brakes.
Steering is, but you can, since you have a view on the namespace of all the engines, you can send, basically write data back onto them, and the code could react to that. So you can change, tune a parameter or whatever. In this case, the most brute force one is a single global flag that says keep running or stop.
Yeah, and there's actually, in terms of steering, there's two ways to do it. There's this way with the thread, and then you just write things and kind of hope that you don't have race conditions. There's a version where you basically take the inner loop out of, rather than the last step of your MPI script be simulation.run, you stop there and then the version in IPython is you stop there, and then in IPython you do, simulation.step 30, simulation.step 1, and then you have easy steering. Another version, depending on if you only need monitoring, there's actually, so just like we've got DisplayPub where you publish representations of things, there is also a data publication API. So you could have it run, and then it actually, as it goes, publish, so that the client doesn't need to ask for the data. The engines can actually send, without the client requesting it, the engines can send intermediate results. Right, getting a handle on the socket would be a bit tricky, but you could do it. Yeah, and you would probably want to do it, if you're doing a non-trivial MPI simulation, you would probably want to do an MPI gather and then get it from one.
We have that example, actually, the alternate. I don't know if
it's not here, but yeah.
In the official docs for IPython, there's a directory that has parallel examples and has both variants. It has the polling variant with threads, and it has the pushing variant where we do an MPI gather reduction on the rank 0 MPI node, and then send that bit with the IPython API. So the idea is do the gather with MPI and then do the publish back to IPython with IPython.displayData. So you can combine the two. That one requires modifying the MPI code more. This one, there's no modification, you're just grabbing, but you ensure consistency because now you know exactly where in your MPI state you're doing things. And you can have higher speed because you're doing your reductions with MPI APIs. Which one do you use? It depends. This one's a little bit easier to do, but it's more limited in performance. And if you look carefully at the code, there's a try except because you may get data from different time steps from different nodes.
There's not a try except in the publication one because it always gets the right answer.
Exactly. No, yeah. And in this one, you have to be a little bit careful because you're not guaranteed consistency. The other one, you have guaranteed consistency, but it's a little bit more work. It depends.
Yeah, and the coordination using IPython to step is kind of in between, because you know everybody's in the same state, so you pull in between doing steps, so you know everybody's in the same state, you know your data is consistent, but you don't, but you need to do everything explicitly. Yeah, so there's this data, this publish data call that is from, where's DataPub? This DataPub API lets you publish arrays and things so that you can get results that aren't representations, right? So I could do plots, I could publish figures, but that just gets PNG data. I couldn't publish a NumPy array without serializing it to JSON or something. So with DataPub, I can publish the actual array itself. So you can have you can have side effects that are not representations of objects, but objects. Yeah, and we have examples in the IPython repo of things including an MPI 2D wave solver, and then the same example rewritten with 0MQ for the interconnect instead of MPI. The 0MQ version is actually faster, not because MPI is slow, but because writing slow MPI is easy. And yeah, and I wrote them both in an afternoon, so they're not exactly super clever MPI. Yeah. Uh-huh. Uh-huh. Mm-hmm. Yeah. I don't think that's going to be in scope for the project, just because you basically need to re-implement everything. And essentially I think there are better tools for that kind of thing than IPython. Yeah, so
It would be necessary to get there.
yeah, it's kind of all about assumptions, right? It's the more assumptions you can make, the better a tool you can. So if you've ever seen the code that is IP cluster, which is the only assumption is I start a process somewhere somehow, it's kind of a nightmare because it's abstractions on top of abstractions on top of abstractions that allow it to be the same interface for PBS and SGE and SSH and because IPython is designed to work with basically no assumptions other than there's a process somewhere, I think it would be simpler to actually build something else that works with the MPI, works with an MPI environment, rather than getting IPython to behave that way if it can make the right assumptions. Yeah, so you could. Yeah, there's a reason that IPython copied the async result and from multiprocessing that pool, and there's a reason why I'm writing a concurrent futures API for IPython parallel, so that it's interchangeable at an API level. So what we do want is to define a good enough API at the client level. So rather than the IPython cluster being able to use all these different things, maybe you write another client, and that client conforms to a similar API, but actually does, because all this logic of I'm doing MPI stuff, or all this logic of doing things on all the engines actually lives in the client. It's not in the cluster or anything. That's just message routing. So you would write an alternative client that talks to the different engines. And yeah, I think such a tool can exist, and I think matching the IPython parallel API would be a reasonable thing if you like it, if you think your users would like it, and then just having a client that's similar. So you could move, rather than IPython somewhat magically being able to behave better, you could have an alternate object that has a similar API, so that you, instead of from IPython import parallel, you do from, I'm faster because it's MPI import parallel. I think that's probably more feasible than getting that logic into IPython. Would be my guess. Yeah.
Basically, I'm trying to understand what you mean by I'm faster because of MPI. Because you're talking to TCP protocol here and MPI protocol is
It's not just TCP. It's the order n. So doing something on every engine is an order 2n operation, right? Because the client just says, it says for every engine do something, and then the scheduler relays those messages out. So that's if you wanted to do more efficient, do something everywhere. If the client, for instance, it would be to actually broadcast the commands, and maybe who knows what your inner loop might be doing some weird polling on MPI buffers or something. And so you actually use like binary spanning trees to distribute the commands, so that you can minimize the number of expensive messages that IPython sends. You can't minimize the number of messages IPython sends. So there's a baseline. And I do have plans for at least using 0MQ's broadcast primitives for schedulers to make it a bit better. But it's never going to be comparable to using MPI for all communication. And it's not just TCP versus backbone. There aren't any parallel primitives. IPython really is a multiplexing design. It's not a fundamentally parallel design. There aren't any ensemble operations at all of any kind. All right. Any other questions? What are we doing? We've got 20 minutes. So another example, which is in examples Wikipedia, say with a parallel crawler. This is an example that uses the IPython widgets and D3. The force-directed graph stuff was written by John, I think. Is that right? Yeah. So I'm going, what this example is going to do is it's going to take, you give it a page, the title of a page on Wikipedia. It's going to walk the links from that page and then build a graph. It's going to build a big graph with network X of all those links. And then it's going to build a small graph with D3 because D3 doesn't like big graphs of the kind of important nodes on Wikipedia for a given area. Oh, right. I was going to do that after that. Yeah. Let me see. This is going to be fun. Terminal window. All right. So I'm going to show you the configuration. So the way I started the all those engines on the cluster was I just clicked the start Dirac with 50 engines. So if I show my IPython configuration for the Dirac profile, I have start the controller with SSH on Dirac. Start the engines with an SSH proxy, which is a terrible name, but what it means is it means SSH to that cluster and then call IP cluster engines. So there's IP cluster start, starts a controller and some engines. IP cluster engines is the same thing, but minus the controller. So you can actually, if you want to set up a cluster, you can do, so if I do locally IP controller profile test. So there's my controller. And then I can do IP cluster engines profile test. And there I've got, I just added some engines. I can kill them. All my engines will go away. I can start some more. Yeah, so now I've got engines 5 through 8. So what SSH proxy does is it means SSH to Dirac and then do IP cluster engines profile Dirac. And then IP clusters, this is tell IP cluster start to use SSH proxy and tell a controller to use SSH. And then if I SSH Dirac, and then my configuration on that machine is basically IPs and use start engines with MPI. That's all the config I used to start all those engines with MPI and everything. So what I'm going to try to do is add a couple local engines with MPI. Oh. I'm going to start engines on this computer with MPI, but connect them to the cluster that's on the remote machine. So that would be IP cluster engines. Start them with MPI instead of SSH proxy. And then N4. And let's go back to the memmap example. And let's check out our engine hosts. Let's see what happens. Nope. Let's give him a couple seconds. My controller is on Dirac, yeah. Oh, it's no. No, that's not the issue. I do actually know what the issue is. Let me try it without MPI. IP engine. Oh, duh. IP. Let's try just one. Profile. I did miss this, which was important. Dirac. I think I need that. No, so the SSH and everything, all those only affect the IP cluster script. The IP cluster script itself calls IP engine, which always just starts an engine. Here, now, me. So let's see if that works. Registering with controller, it's not working. Oh, it is working. That's a surprise. ID 51. Engine hosts. Nope. I shouldn't. It should just know. Well, it registered, but didn't really register. Anyway, it almost worked. The engine thinks it worked. This? No? Oh, it's because it's EAL, yeah. So I need, let's make this clear. Sorry for shouting into the microphone. I need to run this again. I do not need to run this again. Yeah, well, it's because of this no assumptions thing. So if I've got TCP ports, I can add engines from anywhere. And if you got SSH tunnels, like, that covers a lot. And IPython will set up the SSH tunnels for you. Correct. Right. So what this will do, because this is the memmap one. This one will still work and should take basically the same amount of time, because it's still going to send it. So I would need the key. So I skipped this stage of mapping kind of data stores, data sources to lists of engines, because they were all in one. If I had multiple MPI universes and I wanted to use the MPI one, I would have to still build this dictionary and have for each key every MPI universe, and then run the broadcast once for each MPI universe. But this should still work. Let's just, I didn't want to do that. Whatever. So after that guy finishes, it should just, why is this one so much slower? Didn't I do the same thing? Yeah, and let's see, good old 51. Yeah, so he also got the same thing. And because of the way memmap worked, a branch that didn't have any effect last time is, if the host is here, don't even send it at all. Just write it to a file. If you don't have MPI and PBS set up for, like, so when I was a grad student, we had like 7 just desktop machines. They had an NFS file system, but no other connection than that. So I would start clusters with, and they weren't even all running the same OS. So I would start clusters with SSH and work fine. Sure. Yeah, or you could use it for, you might use, depending on, so a lot of people use this, use this with Star Cluster. Do people know what Star Cluster is? Star Cluster is a Python wrapper out of MIT, a Python wrapper around the Amazon EC2 API, so it makes it easy to specifically spin up Amazon clusters with the entire scientific Python stack. And there's a plugin in Star Cluster for IP cluster, so you can spin up your big EC2 cluster with the notebook and an IPython cluster all set up already. If you don't have Star Cluster, for instance, if you have your own AMI, getting getting your EC2, you might manually spin up multiple EC2 instances and talk to them explicitly with heterogeneous. So I start IP engine over here, I start IP engine over here, and then make them talk to each other. Yeah.
Earlier we talked about MPI mortality being fairly poor. When goes down, what happens?
Well, so as you noted, as you saw, there's a gap of 50. That's when I started an engine that actually worked, but I thought it didn't, so I killed it. That's one thing that happens. So an engine has already died in this cluster. Let's try. So my engine, E equals RC51. Where was... Let me grab... I can never type this one from memory. I'm going to segfault my engine. No, because there are too many scripts that call sys.exit that if you run that script, we don't want it to exit IPython. So we actually catch system exit. You can do os.exit, which is a real exit, and then that doesn't get caught. But let's do it for reals. Let's actually segfault. So let's do AR equals E to apply. So that guy's waiting. So this is my engine. Here, he segfaulted. Oh, why is... Killing engines when it's live never works. Is that going to wait? Yeah, it's going to wait. So it should raise... What did I do? It should raise like an engine died error. I wonder why it didn't. I don't really know why it didn't. Ah, it takes a long time, that's why. I don't remember. It's like a 1 to 3 seconds or something. It might take 5 heartbeats, which would be 15 seconds. Right, so I got an error that was the engine died. So what's the state of my cluster? Can I create my eall engine hosts, and 51's not there anymore? I can do my broadcast again. And I get a key. Oh, I need to rebuild host engines. Yeah, so my host map no longer has my dead engine. So I've got, that's a good question. Well, I got a key error. Engine 51 is gone. Yes. Yeah, 51. So engine 51 died. AR, yeah. And if I still have a handle on the engine, right? E.apply sync. I get an index. That should probably be the same as the key error. Yeah. So the key error should probably be an index error. But yeah, so there's no such engine, so I can't, if I keep trying to use it. And anything that I had submitted, theoretically, anything that I had submitted in between the engine dying and the cluster being confident that it died, all of those async results would fail with engine died. The same thing here. It can't. So let's. All my engines are with MPI. We've got 5 minutes left. Let's try. Let's hop over to. So tasks, load balanced views. So I got my load balanced view. Where did die go? So fail. Def. So this is a task that will fail. So I do apply sync. Actually. So I've got these 4 PIDs, except. So let's do if not. So this will fail on every engine except for one. I failed on. So apply. So that guy fails, he fails, he fails. He's okay. So I can, the load balance scheduler actually does implement quite a bit of logic. And among those things are retries. And this is the cost. So we talked earlier about load balanced view, about the fact that apply takes star args, double star keyword args instead of a tuple and a dict. And the cost to that is we can't specify arguments that are meant for IPython in apply. Everything gets passed to the function. So the control of how apply behaves is on attributes on the view. So actually, there's a simpler way. So lbv.retries retries equals 5. Fail. So I just called this apply sync fail, 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 fail. So what that did is it sent it to the load balancer. Load balancer assigned it to someone. It failed. It raised this exception. The load balancer said, that guy failed, but he still has some retries left. So send it again to someone else. So that this is, and if you do this, if instead of fail I use die, it would retry segfault. We're at the end of our time. Let's just do it. Where's die? Yeah. So this is one way to shut down the IPython cluster. It will never send it to the same one. The same one it gets blacklisted. So if it fails, if it always fails, it will get to an impossible state. You'll get you can get an impossible dependency failure that I can't assign this. You can also set a timeout so that it will, if it takes more than 10 minutes to assign this function, just give up. There's actually quite a bit of logic in the load balance scheduler. But let's just, to finish it up, since we've only got 2 minutes left, let's just kill them all. And I guess in about, whatever it was, 15 seconds, maybe 30 seconds, it will say that they all died. No, because it will apply sync, will raise on the first exception. And the timeouts, so they're all dying at the same. Oh yeah, it might take a minute. That's a good point. Yeah, this may take a little while. We can have time for questions while they die. Oh right, I got distracted. Force directed graph. Yeah. Oh, I just killed my cluster though. Let's just start another one. It's a good. Nope. See, it's gone. Yeah, I will stop drag. Let's do. It might be okay. I'm in the middle of killing that guy, but you never know. All right, so this is some boilerplate to parse, get links to other Wikipedia pages from a Wikipedia page. This is add nodes to a graph, setting some default things for D3. Add links from a given node, I'll take all the links and update the graph. And Wikipedia graph is a big thing that populates a network X digraph, directed graph, and then creates this eventful graph, which is the lovely thing that John wrote, which is using the widget system and traitlets to, when I update the graph, it actually updates the graph on the page. So I can add nodes, and just whenever I add nodes, I don't need to republish anything. I don't need to call display. I just add a node on the graph, and then it adds a node on the graph in the page. So this big old thing just takes a node, finds all the links, adds them to the graph, and then adds kind of the interesting ones, which is the hardest part of this demo, is figuring out what the interesting ones is or would be, and then adding those to the eventful graph. So let's just create a Wikipedia graph for SciPy. Cross our fingers. So there's SciPy, software developer, and so this is, yeah, and this is happening in parallel, right? This is just, it's one of those cases where it's map async. That's the whole thing. And the size is proportional to the number of pages that I've visited already that link to that page. I think that's all it does, because once you get a lot of nodes, then D3 gets real sad. Let's see, Austin, Texas. Right, and so these are the number of nodes in my network X graph. So I've got two graphs. I tried doing it with one graph, but D3 just falls down right away. Because after one step, I've got 40 nodes, and it struggles with 50 or so. But yeah, so it's just give me some links from a page, and then create a directed graph of all those links, and then all I'm doing is, in this is, when I find, this is my if a node is interesting, which is to say if there are at least three other pages that link to that node in the real graph, then I add that node and basically its connections to the eventful graph. And all I'm doing is doing add edge and add node on the eventful graph, and setting its size. And just by setting those attributes, I'm updating the SVG on the page. So we can do it with a couple more. It'll be fine. SciPy, Python. Right. So we got again interactive, async, parallel, etc., etc. I'm sure I could filter out some of the less interesting pages. Yeah, now it's getting sad. Well, it did okay. Not too bad. Right? Perl's over here. JavaScript's over here, all alone. Yeah, simple. We got Fortran.
Fortran makes an appearance in the mod as well.
Yeah. Yeah. So that's about all we've got time for.